this video, we're going to be introducing some new terminology about our sequences, as well as a theorem based on a couple of these properties. So the first definition we have is for a monotonic sequence. So a monotonic, you can think of kind of breaking this down, mono meaning one, tonic, okay, one tone. This is something about one direction. This is talking about a sequence being either increasing or decreasing. Okay, so something that's monotonic is either going to be increasing or decreasing. Something that's not monotonic is neither increasing nor decreasing. Maybe it's bouncing around a little bit. So when we say that a sequence is increasing, the definition here would mean that an is less than an plus 1 for all n greater than or equal to 1. Okay, so the nth term is smaller than the n plus 1th term, meaning you'd have a1 is less than a2 is less than a3, etc. Okay, so just to give us a little picture, we have our nth term here is always going to be less than the n plus 1th term. Our sequence is going to be decreasing if an is always bigger than an plus 1 for all n greater than or equal to 1. So this means a1 is bigger than a2, is bigger than a3, etc. Okay, so we always have that our nth term here is bigger than our n plus 1th term. Okay. So what are some additional definitions that we have? We'll go through some definitions and then we'll start looking at some examples of sequences that have a mix of these properties. Our other definition has to do with a sequence being bounded. So we say that our sequence is bounded if the sequence is both bounded above and bounded below. That means that our sequence stays within some restricted range. Okay, so let's just go over these specific definitions of what it means to be bounded above and what it means to be bounded below. Well, a sequence is going to be bounded above, okay, if there is a number, let's call it capital M, so that the terms of our sequence, an, are less than or equal to that number m for all n greater than or equal to 1. Okay. We have our sequence being bounded below, okay, if there's another number, we'll call it little m, lowercase m, so that our sequence is always bigger than that little value for all n greater than or equal to 1. Okay, so just to give us a picture here, if there's some number here, m, that our sequence always stays under, then we're bounded above. And if there's some number, let's say little m here, that our sequence never goes below, okay, then we have something that's bounded below. And if our sequence stays between two different values, okay, then our sequence is considered bounded. Okay, so I've chosen to draw ones here that are neither increasing nor decreasing. I've had them jump all around, but we know we could also have something that stays here bounded, but happens to be something that increases or decreases. Okay, so let's look at some examples on how we can determine if a sequence has some of these properties. So our first example is the sequence whose nth term is an equals 1 over 2n plus 3 monotonic. Is it bounded, and why or why not? Okay. Well, remember the question, is it monotonic, is saying, is it increasing or decreasing. Okay, and it might help for us to write down the first few terms of this sequence. So notice that when n is equal to 1, we'd have 1/5. When n is 2, we'd have 1/7. When n is 3, we'd have 1/9. Okay, so it looks like our values are getting smaller and smaller. The denominator here is getting bigger, which means 1 divided by that value should be getting smaller. So we'd say yes, it is monotonic. Okay, since the sequence is decreasing. And then we want to show a little bit more specifically why it's decreasing. Okay, so that means we need to show that an plus 1, okay, the n plus 1th term, is always smaller than the previous term. Okay, we'll notice that our an here is equal to 1 over 2n plus 3. an plus 1 would be equal to 1 over 2 times n plus 1 plus 3, okay, which equals 1 over 2n plus 5. Okay, so then I have an inequality that I want to set up and show that 1 over 2n plus 5 is actually less than 1 over this 2n plus 3. So notice that for n greater than or equal to 1, 2n plus 5 is definitely bigger than 2n plus 3. Okay, so the reciprocal here, 1 over 2n plus 5, will be less than 1 over 2n plus 3. So when I take the reciprocal, that's going to switch the direction of my inequality sign. Okay, so we do have an plus 1 is less than an for n greater than or equal to 1. Okay, so we were able to show that it is decreasing. So what about being bounded? Okay, well, notice that our terms themselves, okay, if we look at this 1/2, 1/7, 1/9, they're always positive. So we can say it's definitely bounded below by 0 here. Okay, looking at these terms, we see we're always going to be dividing 1 by some number that is bigger than or equal to 5. Okay, so this is definitely less than 1. You could find an even closer bound if you like. It looks like the values are actually always less than or equal to 1/5. Okay, so this is decreasing. 1/5 is our first value. The values get smaller and smaller and smaller after that. So we could use 1 as our upper bound. We could also use 1/5 as the upper bound. Really anything that's bigger than 1/5 will also work. Okay, so it is bounded, since it's bounded below by 0 and bounded above by 1/5. Okay, so that gives you an idea of something that fits both of those conditions. So let's look at another example. So what about the sequence whose nth term is an equals -2 to the n plus 1, where n is greater than or equal to 0? Is this a monotonic sequence or a bounded sequence? Let's look at some of our terms here. So when n is 0, this would be -2 to the 1, or -2. When n is 1, I'd have -2 squared, so that would be 4. When n is 2, let's see, I'm going to have -2 cubed, so that'll be -8. So notice that the pattern here, I've got -2, 4, -8, then I'm going to get 16, -32, etc. So just looking at these terms, is this monotonic? Well, I've got -2, then I increase to 4, then I decrease to -8, then I increase to 16, then I decrease to -32. So it's not monotonic. Okay, it's not increasing and it's not decreasing, it's bouncing around. It might even help us to draw a quick sketch of our sequence here. So we notice that at n equals 0, we're at -2 here. At 1, it's at 4. At 2, -8. At 3, it's all the way up at 16. So we see that we're bouncing around, and we're, as we go out here with bigger and bigger values of n, it's going to be bouncing further and further at larger and larger positive and negative values of n alternately. So it's also not bounded. Okay, so we can kind of see that in terms of what the limit will look like. It will go to infinity and negative infinity alternately. Okay, it looks like in the starting with -2, these values, -2, -8, -32, are going off to negative infinity. The term starting with 4 here, 4, 16, the next term would be 64, those would be going off to infinity. So it's bouncing around, and it's not going to be stay within any kind of strip between two numbers. Okay, so that's something that doesn't satisfy either one of those conditions. So let's just look at one more example. Is a sequence whose nth term is an equals 2 to the n monotonic or bounded, and why or why not? So let's just write down what this sequence looks like. So 2 to the 0 would be 1, 2 to the 1 would be 2, 2 squared would be 4. Okay, so it looks like this is our sequence here. So is this monotonic? Well, yes, it is monotonic. It looks like it's strictly increasing here. And then we'll want to show with some inequalities that we've met the definition for increasing. So we want to show that an plus 1 is always bigger than an. So notice that our an plus 1 equals 2 to the n plus 1, and an equals 2 to the n. Okay. I can say that 2 times 2 to the n is definitely bigger than 2 to the n, okay? And this 2 times 2 to the n is 2 to the n plus 1. Okay, so we can see that that inequality is satisfied, showing that the sequence is increasing. Is it bounded? Well, no, because it's not bounded above. It's only bounded below. Since the values here are going to keep increasing, we do not have an upper bound, but the values are all positive, so we can say that 2 to the n is always bigger than 0, but we don't have an upper bound. Okay. So what's kind of important? Why are we talking about these properties in particular? So whether a sequence is increasing or decreasing, and whether it's bounded above or bounded below, some of those properties will come into play when we start discussing some of our convergence tests for series later in chapter 11. But we also have the following important theorem that talks about the connections between these two properties and sequence convergence. So we have something called the Monotonic Sequence Theorem, which states that every bounded monotonic sequence is convergent. Okay, so what does this mean? Let me write that out in a little more detail. This says if a sequence is bounded, meaning bounded above and below, okay, and it is either increasing or decreasing, it must converge. That's what this statement is saying. Okay. So if you have the properties of being bounded and monotonic, bounded being staying within some strip, and either being increasing or decreasing, the sequence must converge. So let's just draw a picture and think about why that is. So if you're, let me draw some bounds here. Let's say I have to stay between those two red lines, and my sequence is increasing. Okay, well then it has to be converging to some value. It can't exceed this upper bound here, and it's always getting bigger than the previous value, so it must converge to something. Similarly, if I have my sequence having to stay between two bounds and being decreasing, oops, let me use my other color here, then again that sequence has to converge. Okay, so we just want to make a note about this. So note the following. This statement doesn't say that just because a sequence converges, it has these two properties. So this statement doesn't go the other way. It is possible to converge, for a sequence to converge, without being bounded and monotonic. It's not possible to not converge if the sequence is bounded and monotonic, but you could have a sequence that converges without being both bounded and monotonic. So just to give some examples of these situations, I could have something that's bounded, maybe it's bounded below, and it decreases, okay, and does converge. So this is not bounded. It's not bounded above, but it does end up converging. I could also have something that converges but is not monotonic. Okay, we've seen some examples like this. You could have something maybe that oscillates, but the oscillations get smaller and smaller and smaller, and so it still converges. So this is an example of something that's converging but is not monotonic. Okay. So important thing to note here out of these statements. Okay, but if a sequence is bounded and monotonic, it must converge. And you'll get a chance to apply this theorem in one of your homework problems. Let me know if you have any questions.